All right, we are going to talk about section 3.3. This is rules for differentiation. Whoops, imagine that looked like an N. All right, so this is usually a day that upsets some students because it is a day of shortcuts to find derivatives. So I'm just going to get right into it. What these things are going to do, what these rules are going to do or help you with is help you avoid using the definition of a derivative, the four-step process to evaluate derivatives. So the first rule here is this: if f is a constant, the derivative with respect to x is equal to, I guess I wrote is 0. Okay, so in mathematical symbols, that is d dx of some constant c is equal to 0, right? And so just to give you a quick example of that, if I gave you that the function f of x was equal to 5, then we could write that f prime of x was equal to 0. And this should sort of make sense, I hope, if you were to sketch the graph of y equals 5, and then I asked you what was the slope of the tangent line at any point on that graph, you'd be like, well, it's always 0 because the slope of the line is always 0. All right, so we've sort of talked about that one. Let's get into some rules that are more interesting. Before I give you this next rule, see if you can figure out what the pattern is. I'll give you some functions and some derivatives. So how about this? Y is equal to x squared. Y prime is equal to 2x. And throughout this lesson, there will be times where I tell you to pause and see if you can come up with a pattern, because if this was in class, then I'd be doing that. I'd be stopping and asking you to think about the pattern. So I think you'll benefit some if you try to pick up on the patterns here. So anyway, all right, so the first one, x squared is 2x. Y equals, how about this, 4x to the 5th. The derivative of that is equal to 20x to the 4th. I'll give you another one here. Y equals, 2x to the negative 3. So y prime on that one is negative 6x to the negative 4th, right? So see if you can figure out the pattern there. Hopefully you gave it some thought. Here's the rule. Rule number 2. It's called the power rule. And it says this. I'm not going to write it out in words, I don't think. It says for any positive or negative power of x, this is the rule. The derivative with respect to x of x to the n, again, where n is any negative or positive number, is equal to n times x to the n minus 1. In other words, the rule is multiply by the power and take 1 away from it. Okay, so you can see up here, we take the 2, multiply by 2, and then subtract 1. So I get a power or exponent of 1. I guess I should say exponent. Okay, multiply by 5, take 1 from the exponent. Multiply by negative 3, take 1 from the exponent. Okay, so that's the pattern for the power rules. You can imagine how this saves you a ton of time in finding derivatives. Let's do a few examples here. So I already gave you a couple up here, I guess. Let's see if we can do any that are sort of interesting and that build on that. So how about this? Y equals the square root of x. Well, this is one that if you had to use the four-step process, it would be a lot of work. You'd have to end up multiplying by the conjugate to get a factor of h in each term. But what we can do is just turn it into a power rule problem. So we can just write this as x to the 1/2 power. And then dy dx, the derivative, is just going to be equal to times by the exponent. So 1/2. Subtract 1 from it. That'd be negative 1/2. And there is your derivative. Okay. Here's another one. How about this? Y equals 3 over x squared. Again, this is a situation where the definition of a derivative is going to be a lot of work. But what we can do is we can rewrite this as a power rule situation. So this will be 3x to the negative 2. Okay. So when I take the derivative with respect to x, I'll get negative 2 times 3, which is negative 6. And then subtract 1 from the power, that'd be negative 3. And then you could write it in, back in rational function form, but you don't have to. So you could, I guess you could write like this. That'd be fine. But this answer is okay too. So there's the power rule. Save you a bunch of time. Let's go on to rule number 3. Okay, this is the constant rule. Okay, so in this, I'm going to write this part down. So if u is a function, you know what? No. We're just going to use f of x. I don't know why the book uses u. Let's suppose f of x is a function, and c is a constant. Then we can write this for our rule. So if I want to take the derivative with respect to x of f of x, of c times f of x, so some constant times f of x, that is equal to c times the derivative of the function. Okay, in other words, you can just derive the function on its own and then multiply by the constant. I'm running out of space on the sheet of paper, but just to give you a quick example of this, if I gave you that f of x was equal to, I don't know, 17 x squared, and I said, all right, we'll take the derivative of each side, d dx of the left, d dx of the right. Okay, here's what you could write. Derivative of f of x, I'm just going to write that as f prime of x. Then I can take the 17 out in front, so I'd have 17 times the derivative of x squared, the d dx of x squared. So let's just write that. Okay. What's the derivative of x squared? Well, that's a power rule problem. 2 times x is the derivative, so I end up with 17 times 2x, so I end up with 34x. This rule is not that impressive or useful in this problem because you could have just used the power rule on this one, but it will become more and more useful as the problems get more complicated, and especially because this rule showed up in limits, it shows up in derivatives, it's going to show up in integration as well. It's really a useful rule. So let's keep going. There are more rules. Let's go on to rule number 4. Number 4 says this. This one I guess I am going to use their notation. So let's suppose u and v are functions of x. Okay, so suppose u and v are functions of x. Then we can write this, that the derivative with respect to x of u plus or minus v is equal to the derivative of u with respect to x plus the derivative of v with respect to x. Okay, so in other words, if you have the sum of two functions, you can take the derivative of each one individually and then add those derivatives together. Okay, so just as a quick example of this, what you can do is take f of x equals 9x squared minus 4x plus 1. And I can apply several rules here. This one would be a power rule. This one would be a power rule as well. The power is 1. Okay? And then this one is the derivative of a constant rule. So what I can write then for the derivative is 18x minus 1 times 4, subtract 1 from the power, so that'd be 4 times x to the 0. Sorry, I didn't write x there. 18x. So 4 times x to the 0, but anything to the 0 power is just 1, and this is going to be plus the derivative of 1, which is 0. So when I clean this up, it will end up just being 18x minus 4, because again, anything to the 0 power is 1. So there's your derivative there again. So the sum and difference rule, quite useful. Okay. I give you this one. You should try this one. See how, and then, so pause it, try it, and then see how it goes. I'm going to run through it real quick here, but the function that I'm going to give you is going to be different. It's going to be p equals t cubed plus 6t squared minus 5/3 t plus 16. Okay, so this is a function p of t, so like maybe a position function or something like that. It doesn't really matter, but we're using different variables here. So then I'm going to write, so you should pause now and try and take the derivative, see how you do. I'm going to write this, dp dt is equal to 3t squared plus 12t minus 5/3 plus 0. So I'll just leave it at 5/3. Okay. So the rule applies whether we're using x's or t's or whatever our independent or dependent variable is. right? So hopefully that went well. I'm going to answer one type of question here. That is going to come up. Well, I should write it down here. So I'm going to find the horizontal tangents. All right, given this function. Y equals 5x cubed minus 3x squared plus 1. All right, find the horizontal tangents. Let's think about what that means. Horizontal tangents are where the tangent line is horizontal, obviously, but the slope of the tangent line is 0. So in other words, that's where the derivative is equal to 0. So if we want to know where the derivative is equal to 0, and again, we're doing this analytically, we're doing it algebraically. If I want to know where the derivative is equal to 0, I need the derivative, and then I'll set it equal to 0. So let's find the derivative. It is y prime is equal to 15x squared minus 6x. 2 times 3 is 6. Subtract 1 from the power is 1. All right, then derivative of 1 is 0. Okay, what I want to know is, when is this equal to 0? Because that's where the horizontal tangents will be. So I want to solve this equation. 0 is equal to 15x squared minus 6x. All right, easiest way to solve a quadratic is to factor it if you can. And what I notice is that I can take a 3x out of this term. I can factor a 3x out of this term. So I get 0 is equal to 3x. Let's just try that again. 0 is equal to 3x times 5x minus 2. Okay, so again, we're going way back to algebra 1 and algebra 2 here. We're solving a quadratic. I'm going to do this. When is 3x equal to 0? When is 5x minus 2 equal to 0? Okay, well, if I solve this for x, I get x equals 0. And then I'm going to add 2 and divide by 5, so I get x equals 2/5. Okay, so that's where my horizontal tangents are, is x equals 0 and x equals 2/5. It'd be worth your time to take a look at the graph of that, of the original function, and confirm that you have a maximum or a minimum at, any horizontal tangent at x equals 0 and x equals 2/5. Okay, and I think that is going to pretty much wrap up this video, and we will talk about undoing the derivative in the next video.